Hello, this is Dr. Pramod P. And today we are going to discuss about an important topic, and that is operations, axioms, and theorems of Boolean algebra. Now, what is Boolean algebra? The term algebra refers to the rules of a number system. Basically, it defines the operations that are legal to perform on that system. Once the rules of the systems are defined, then it can be used to perform powerful mathematics such as solving for unknowns and manipulating into equivalent forms. Boolean algebra was introduced in 1854 by an English mathematician, George Boole, and he presented an abstract framework for a system that contained only two states, that is true and false. As you may be knowing, in binary system we have ones and zeros, that is true and false. Now the important operations in Boolean algebra. Then the core operations are conjunction, disjunction, and negation. Conjunction means it's equivalent to AND operation. Disjunction means it's equivalent to OR operation, and negation refers to NOT operation. From the core operations, we can develop more sophisticated operations, and they include logic functions such as buffer, NAND, NOR, XOR, and XNOR, and also arithmetic logics. And engineers primarily use the term AND, OR, and NOT instead of conjunction, disjunction, and negation. A statement of truth about a system that is accepted by the user is referred to as axiom, and we have 5 main axioms in Boolean algebra. The first one is axiom 1, and axiom 1 means it's about the Boolean values. So a variable a will be having a value a equal to 0 if a not equal to 1, and conversely a will be equal to 1 if a is not equal to 0. Axiom 2 states about definition of logical negation. Yeah, that is if a equal to 0, then a complement equal to 1. Conversely, if a equal to 1, then a complement equal to 0. Then axiom 3, it's about definition of a logical product. Logical product means a and b. So a and b is equal to 1 if both a and b equal to 1. A and b equal to 0 otherwise. Axiom 4 is definition of a logical sum, that is a plus b, or a or b. A or b equal to 1 if a equal to 1 or b equal to 1. So a or b equal to 0 otherwise. Then the fifth one is definition of logical precedence. So precedence means the operations which is having a more importance. So NOT gate precedes over AND gate, and AND precedes over OR gate. Now the theorems in Boolean algebra. The important theorems in Boolean algebra are listed out here. Number 1, De Morgan's theorem of duality, identity. Second one, then null element, idempotent, complement theorem, involution, commutative property, associative property, distributive property, absorption, uniting theorem, and finally De Morgan's theorem related with complements. Now the first one, De Morgan's theorem of duality. Duality states that the algebraic equality will remain true if all zeros and ones are interchanged and all and or operations are interchanged. The new expression is called the dual of the original expression. An example for a duality theorem. Let's consider the original expression a dot 0 equal to 0. That is a and with 0. That is equal to 0. The dual can be obtained by interchanging zeros and ones and operation with the OR operation. Therefore, the dual expression over here is a plus 1 is equal to 1. The Boolean algebra theorems can be proved by simply testing the theorem using every possible input code. This is called proof by exhaustion. Now, what is the proof by exhaustion? It's a method by which we will be directly assigning value to the variables. Two possible values are zeros and 1. Then we will verify whether the expressions are okay or not. At first, let's consider the original expression, that is a and 0 equal to 0. Then substitute a equal to 0 then we will be getting it as 0 and 0 equal to 0. And now the dual, and for the dual the expression is a plus 1 equal to 1. So let's give a is equal to 0, so it will be equal to 0 plus 1 equal to 1, and again if a is equal to 1, it will be like 1 plus 1 equal to 1. So the dual expression is verified using proof by exhaustion. One consideration when using duality is that the order of precedence follows the original function. The axiom for precedence states the order as not, and, or. That is, not gate is having highest precedence, followed by and gate and or gate. However, this is not necessarily the correct precedence order in the dual. For example, consider the function f is equal to ab plus c. So a and b plus or c. So that's a function. The dual of the original function is fd equal to a plus b into c. Here the operation between a and b is having highest precedence, since in the original equation or original expression we have the operation between a and b is having highest precedence. So the dual follows the original equation as far as precedence is concerned. So a plus b will be having highest precedence compared to into c over there. Identity operation. An identity operation is one that when performed on a variable will yield itself regardless of the variable's value. Just for an example, a plus 0 is equal to a itself. A into 1 means a itself. So the gate level depiction is shown over there. The original one is OR gate, and its equivalent is, and its dual is AND gate. So as far as the original is concerned, it is a plus 0, that is a or 0 equal to f, that is equal to a. Then as far as dual is concerned, it is a into 1 equal to f equal to a. Null element. A null element operation is one that when performed on a constant value will yield that same constant value regardless of values of any variables within the same operation. So there is a plus 1 will give you the value as 1, and a into 0 will give the value as 0. Idempotent. An idempotent operation is one that has no effect on the input regardless of the number of times the operation is applied. For example, if we are ORing a many times, the result remains same as a. F will be equal to a. And if we are doing AND operation many times with the same variable a, then also the result will be a. Complement theorem. This theorem describes an operation of a variable with variables on complement. For example, operation between a variable a and its complement a complement, and a plus a complement is equal to 1. So if that's the original expression, its dual is a into a complement is equal to 0. Involution. An involution operation describes the result of a double complementation. Let a be the variable, then a double complement is equal to a. That is, we are complementing a, we will be getting a complement. Then once again, if we are taking complement of a complement, we will be getting a itself. Commutative property. The term commutative is used to describe an operation in which the order of the quantities or variables in the operation have no impact on the result. That is, if the original equation is a plus b, then even if we are writing it as b plus a, it has no impact on the result. So its dual is a into b equal to b into a. Associative property. The term associative is used to describe an operation in which the grouping of quantities or variables in the operation have no impact on the result. That is, consider the original equation as f is equal to a plus b plus c. That is 3 input OR gate. So that operation can be done as a plus b, then after that plus c. That is 2 input OR followed by another 2 input OR, and it can also be done like b plus c plus a or a plus b plus c in bracket. So in short, a plus b plus c is equal to within bracket a plus b plus c, that is equal to a plus within bracket b plus c. So then the next one is its dual. Dual is an AND gate, 3 input AND gate, that is f is equal to abc. So it can be written like ab at first, then into c, and it can also be like bc can be calculated at first, then into a. Distributive property. The term distributive describes how an operation on a parenthesized group of operations can be distributed through each term. So that is, let's our original expression be like a into b plus c. So it can be distributed as ab plus ac. Its dual is a plus bc. So it can be redistributed as a plus b into a plus c. The distributive property can be used as a logic minimization technique. It can be used to put a logic expression into a form more suitable to direct circuit synthesis or to reduce the number of logic gates necessary. Absorption. When the term within a logic expression produces the same output or outputs as another term, the second term can be removed without affecting the result. Thus, the number of logic operations can be reduced. The remaining terms essentially absorb the functionality of the eliminated term. Therefore, it is also called covering theorem. For example, over here, let our expression be f is equal to a plus ab. F is equal to a plus ab means it's essentially equal to a. So even if we are removing the term ab, the output remains as f is equal to a. And its dual is shown over here. It is a into a plus b. Uniting theorem. The uniting theorem or combining or minimization provides a way to remove variables from an expression where they have no impact on the outcome. This theorem is most widely used for the reduction of number of gates needed in a combinational logic circuit. The gate level depiction of the theorem is shown over here. Let our original expression be like AB plus AB complement. So that is essentially equal to A. And again its dual is A plus B into A plus B complement. It's again equal to A. Now the last theorem, which is known as De Morgan's theorem related with the complements, it's very important, and this theorem provides a technique to manipulate a logic expression that uses AND gates into one that uses OR gates and vice versa. It can also be used to manipulate traditional Boolean logic expressions that use AND or NOT operations into equivalent operation that uses NAND and NOR gates. That is, NAND and NOR only circuits can be developed by using De Morgan's theorem. The De Morgan's theorem original expression is f is equal to a complement plus b complement. So a complement plus b complement is equal to a into b whole complement. That is, the sum of complements is equal to the complement of their products. The gate level depiction is shown over here. A and B are given as the input and it is complemented. We will be getting A complement and B complement respectively from the inverter outputs or NOT gate outputs, that they are given as the OR gate input. So A complement plus B complement, it is equal to over there, it is complement of A and B. So in the second row we will be able to find a more optimized form of the representation. From the gate level description in the second row, we can conclude that an OR gate with the inverted inputs is equal to an AND gate. The dual of the original expression is shown over here, that is f is equal to a complement into b complement, that is equal to a plus b whole complement. The fourth row represents the optimized form of the dual, and it can be read as an AND gate with inverted inputs is equal to an OR gate. Example, a simple sum of product form expression, that is y is equal to a b plus cd. Exactly it is a and b or c and d. The logic diagram shown here consists of two AND gates and an OR gate. Let's at first see how to develop an AND only circuit. So for that, at first we will be placing two inverters just after the two AND gates. So in two inverters means basically the result will be same as per the involution theorem. So you will be getting it as a b complement at first on the top, then one more complement means it is a b again, and towards the bottom side it is a cd complement by the first NOT gate, and one more NOT gate or inverter will give you the non-inverted form of the product as a cd. The same circuit is redrawn over here, and here the inverters are just shown by using bubbles in between the gates. Now rearranging the bubbles, that is the inverters, the circuit can also be represented like this. An OR gate with inverted input is equal to an AND gate. So with that concept we can redraw the final circuit as shown over here. That is, we obtained the NAND only circuit by the application of De Morgan's theorem. Let's apply the two's complement law and De Morgan's theorem together. Our original expression is y equal to a and b or c and d. Now just double complement it. The second row, that is equal to, you just double complement the first one. Then you arrange the double complement. So like as shown in the third row. Applying two's complement is over now. Now let's consider we have two complements. The first complement we need to consider, and applying De Morgan's theorem. So we can write the inner part, that is within bracket a and b or c and d bracket closed, then complement. So we need to take that one alone. Then applying De Morgan's theorem, we can write that part as within bracket a and b complement, that's equivalent to NAND gate, and the second part is within bracket c and d bracket closed, then complement, that is cd complement, cd whole complement. So ab whole complement means NAND gate for which the inputs are a and b, and cd whole complement means NAND gate again with the inputs c and d. So these two NANDed, then we will be getting the output y as per this expression. Now let's apply De Morgan's theorem for developing NOR only circuit. Our expression is a POS expression, and it is a plus b into c plus d. Here double inverters are placed at the indicated nodes in order to create an AND gate with its input inverted. The same circuit is redrawn over here, and for inverters bubbles are used. The bubbles are relocated such that we will be having two NOR gates towards the input side, and towards the output side we will be having an AND gate with the inverted inputs. Here the final AND gate with inverted input is replaced by using an NOR gate, because we know AND gate with inverted inputs is equivalent to an OR gate. Thus a NOR only circuit is developed. We have the expression over here as a or b and c or d. So this is product of some expression, and in the second row double complement law is applied, and in the third row some rearrangement has been done so that we can easily apply the steps further. Then in the fourth row, as you may be able to find, the De Morgan's theorem is applied, and finally we will be getting an expression where we will be having the formation of the circuit by using 3 NOR gates. Hope this video is very useful for you. I will come with more designs. Thank you all for watching this video. Have a very nice day.